Hello, I'm Nikhil Kumar, and welcome to Lab 1 of Physics 2211, Constant Velocity. Here's a quick rundown of what I'll explain in this lab report. The main purpose of this lab is to analyze and compare an object that is moving with constant velocity to the results of a computational model. In this lab, our object or system is an expo marker. Our observed model is determined by a tracker, and a predicted model is coded in GlowScript. Some key concepts that we'll need to cover include Newton's first law, second law, and net forces. First, net forces. In constant motion, net forces sum to zero for constant velocity motion. Newton's first law states that an object will continue moving at constant velocity unless acted on by a net external force. If net force is zero, the object's momentum will be constant, and its velocity will also be constant. Newton's second law states that an object's acceleration is directly proportional to the net force acting upon it. If the net force is zero, acceleration will also be zero. These are the equations that we'll be using. So first, velocity update shows that Vf equals Vi plus F net over m times change in t. When net force is zero, velocity final equals velocity initial, showing that velocity is constant, which is consistent with Newton's first and second laws. This is also true for average velocity, as average velocity will also be constant because velocity is constant, and that means that position. We can use this in our position update formula in GlowScript, where we can show the position of the tracker at each moment. Our momentum principle is basically our Newton's second law, which means that when net force is zero, change in momentum is also constant, which means change in velocity is also constant. Our experimental procedure includes recording a video of an expo marker or system rolling at a constant speed in one direction. We'll then import the video into the tracker program and use the track feature to track individual points of motion. We'll create a computational model for predicting the position and get data from it. And we'll create a spreadsheet on Excel to compare predicted and observed data. We'll compare charts of both the data sets and make our final conclusions. Our system is our expo marker, and our surroundings are anything acting on it. So the table, friction, air resistance, and normal force. So this image shows our setup for tracker in the second step of the procedure. After the video is uploaded, we set our calibration, which allows us the tracker to convert pixels to real world units. We also modified our axis because our video was tilted, and so we needed to modify it as so. The red arrow points in the negative x direction, which is the way our marker is moving, and we track the object frame by frame to get position versus time data. So what did tracker give us? Tracker outputted a position versus time graph, which shows that the slope or average velocity is constant, which means that our average velocity can just be computed versus the first two data points, which is negative 0.33 meters per second in the x direction. Our initial position can be found using the first position, which is 0, 0, 0, and our change in time is 0.0333 seconds. So when we put this into GlowScript, this is our first screenshot where we put initial position, initial velocity, and change in time to GlowScript. We also know that the mass of the expo marker is 0.068 kilograms. Their second major GlowScript screenshot is where we put the time of the clip as 0.46 seconds. Our net force is zero, and then we put our velocity and position updates to find the velocity and position of the tracker at each point. So our discussion, what does it say? So our position versus time graph for the expo marker for both our observed and predicted positions. The constant slope shows us there's a constant velocity with no acceleration and therefore no net force. These two, the observed and predicted model, are very close together, showing us that net force was indeed zero. And however, there's still some deviation. So what could explain that? Well, first, friction and air resistance slow down the expo marker, so it could be due to small friction and air resistance. Human errors with trackers, because the tracker program basically the frame rate is limited to 30 FPS, and it can cause errors in calibration and data measurements. So rounding the initial position could also cause some slight deviation in the tracker program. So what if we flip the axes so that negative x and x are flipped? Well, this makes the components in the position and velocity graphs, like their components flip, so they're negative of whatever they would be, which would flip the sign of the slope for position versus time. In our case, since our slope is negative, it would be positive. How many pushes and pulls make a net force? Or basically, how many forces add together to make a net force? We're unable to find this out. However, this does not mean that there's no forces acting in the system. Rather, they balance out and the net force is zero. So what are our conclusions? The predicted and observed models have very similar best fit lines, giving us the assumption that the system had a constant velocity with little to no net force. Thank you.